In this short video, we're gonna try to explain the AC models for MOS in saturation regions. AC model could be a little bit confusing for the beginners, but we're gonna use one MOS example here, try to clarify that. In this AC models, of course, this one kind of ignored the body fact. It has only 3 terminals: gate, source, and drain, and it has one current source. That current source is controlled by the delta of VGS, stands for the change of VGS, and also the current source in parallel with RO. That's in HSpice. In cadence, I remember that was represented as a GDS. 1 over GDS equal to RO. Okay, so let's jump to this MOS example here. Let's say we apply 0.65 volts across VGS. This is a large signal, right? The MOS threshold is about 0.45, 200 millivolts for the overdrive. Now we apply 1 volt across the VDS here. By certain sizing, IDS now is 1 microamps. So there are 2 scenarios. First one, let's change the VGS by just 1 millivolts. So how much IDS can get changed? How much change on the IDS? So that equal to GM multiplied by 1 millivolts. So that's first scenario. Second scenario, we keep the VGS the same, but rather we change the VDS by 1 millivolts. How much change on the IDS? That equals to GDS multiplied by 1 millivolts. When you design, you can later on know actually it's usually when the device is in the saturation region, GM is at least tens of times of GDS. If that's the case, you're going to see that the 1 millivolts on the VGS cause a lot more change in IDS. Right? So as we pointed out here, VGS has way more influence on delta IDS than the delta VGS. And also here we pointed out that when large signal IDS is about 1 microamps, usually, of course it depends on what kind of lens you use for the MOS, but usually RO is in the range of megohms. Thank you for watching. If you liked the video, please give us thumbs up. It means a lot to us.